All right, so lesson 2 of this third chapter is polynomial division. This is where we are, as the title suggests, taking a polynomial and dividing it by something else. We're only going to focus on taking a polynomial and dividing it by a binomial. That's where it's like an x, let's say like an x plus 1, but it is still considered polynomial division. Let's get going. So today's plan is we're going to learn how to divide a polynomial by a binomial. There's two ways of doing this, and we are going to cover both. There's something called polynomial long division, which I'm going to be honest with you, it's more time consuming, but it'll always work no matter what kind of binomial you have. In math 30-1, we actually don't really need to use that one so often. I would actually recommend we more focus on the second one called synthetic division, which is way quicker, but it only works on binomials that only have one x. So if you had if you're dividing by 2x plus 6, you wouldn't be able to use synthetic division on it, at least not easily. We'll expand these ideas into something called remainder theorem as well, which will help us identify the remainder when we divide a polynomial. And that's useful for a few reasons. We'll get to that when we get to that, though. Let's get rolling. So before we start talking about polynomial division, I just want to make sure that we have an understanding of just good old-fashioned long division. So we're going to do a couple long division questions, just like you would have done many years ago in maybe grade 5 or 6 or something like that. So first of all, 129 divided by 4. If we use long division, the way I typically have done it is I write the number I'm dividing, and then I'm going to put 4 on the outside over here. And then I ask myself, okay, how many times does 4 go into 1, the very first digit here? Well, 4 is not going to go into 1. That's not possible. So then I skip and I go, okay, how many times does 4 go into 12? Well, that one we can do. 4 goes into 12 3 times. So I put a 3 up top there right above where the 2 is. Now here's what we do. We go, okay, 4 times 3, that's going to be 12. So I'll write a 12 underneath, and we always subtract away to see where we can go from there. So if I subtract that away, we get 0 from 12 minus 12, of course. And then we have to drop down this next digit to 9. So now you repeat the process. You say, okay, how many times does 4 go into 9? Well, 4 goes into 9 2 times. So I'll put a 2 up here. 2 times 4 is 8. Subtract that away, and we're left with 1. Now, once we get to this point, we have no more digits to pull from. So we ask ourselves one last time, does 4 go into 1? It doesn't go into 1. So what we would say is 129 divided by 4 equals this number up on top, which was 32, but it has something we call a remainder of 1. That's just the number that was left over in the end. What that remainder of 1 is really doing is, yes, when you go 129 divided by 4, you get 32. But the remainder of 1 just basically means you have another 1 that can't be divided by 4, still going to add on top of this. So really, if you wanted to know what this is equal to, it's 32 plus your remainder, which is 1, divided by what you were dividing by in the first place. So 32 plus a quarter, that would be 32.25. That would be the actual answer here. You can always test that in your calculator if you ever want to check. Next one here, a little bit trickier, 327 divided by 12, same idea, go 327, put in a little box, write 12 on the outside here. Now we take this whole number here and we ask ourselves, how many times is that going to fit into 3? Well, 12 doesn't go into 3, so that's kind of silly. We're going to have to skip now to 32. How many times does 12 go into 32? Well, it goes in twice. 2 times 12 is 24. Subtract that away, and you're going to get 8 left over there. Now we need to bring down the 7, so the 7 sits there. Now we ask ourselves, how many times does 12 go into 87? Well, I know 12 times 6 is 72. 12 times 7 must therefore be 84. Yeah, 84. So then I'll say it goes into it 7 different times. So 12 times 7, again, like I said, was 84. Subtract it away. We're left with 3 left over. And of course, 12 doesn't go into 3, so 3 is going to be our remainder. So just to finish this off, we would say 327 divided by 12, equals our answer, which is 27, and then a remainder of 3. If you don't like writing remainder of 3, you can always say plus 3 over whatever you were dividing by in the first place, so 3 over 12. That's a more true representation of what the actual answer would be. So 27 plus 3 over 12, that's going to be exactly whatever 327 divided by 12 actually is. Anyway, moving on, we're going to focus on polynomial division here. So in math 30-1, we will need to understand how to divide a polynomial by a binomial, just a two-piece thing, like x minus something or x plus something, right? So it's important to understand that the remainder is still a fraction of the divisor. So just like on that last slide, on both of those questions where I said, oh, it's plus the remainder over whatever you're dividing by, same with this one, the remainder over whatever you're dividing by, that still happens with polynomials, right? So here's what we got. you can write polynomial division as a division statement in one of two different forms. I greatly prefer this one on the left, but the one on the right works as well. The one on the left says your original polynomial divided by your binomial equals your quotient, which is going to be a new polynomial. That's why I'm calling it q of x. So it's just some new polynomial plus your remainder divided by whatever you were dividing by in the first place. That's exactly how we set up those other ones, right? So it's your answer plus your remainder over whatever you're dividing by. If you don't like that way, you can write it just kind of in terms of what your original polynomial was. So imagine we multiply everything on this left one by x minus a. This gives us our polynomial that we started with equals our answer times by what we were dividing by plus our remainder. I'm going to be honest, I really don't like using that one at all. I don't see what the point is. It doesn't show the division. It just shows what the polynomial was equal to in the first place, but it is what it is. Now, in addition to having two different forms for a division statement, there's also two methods for dividing polynomials, and we need to cover both methods. I'll be honest, on tests and stuff like that, I don't assess both methods. You can use whatever method you want, but there's polynomial long division, which is going to be pretty familiar. It's very much like what we just did with those numbers. But the trouble is it's more time and space consuming. It takes quite a while and it takes up a lot of space. Another method, which I'll show you afterwards, is called synthetic division. This one is, in my opinion, the gold standard here. This is the one I think most of you will want to use. You're more than welcome to use polynomial long division, but I'm going to tell you right now, as we go forward in this unit, you're going to see me pretty much exclusively use this one. But again, you have a choice. They both work. They're both valid. I'll show you both ways. All right, so here's an example. Use polynomial long division to calculate the quotient and remainder in the following problem. And then, of course, down here, it wants us to write it as a division statement. In other words, kind of like the stuff we see in that box right there. So here's how we go about this. It's basically the same thing as what long division was on your old numbers, right? So write the thing you're dividing. So x squared plus 7x plus 17. And let's put that inside of a box. Now, on the outside of the box, we're going to write what we're dividing by. Well, we're dividing by x plus 3. Now, to get this started, we have to think about what this whole x plus 3 would have to multiply by to give us the x squared plus 7x that we see here. Now, the trouble is it's not going to fit in perfectly. There's never any guarantee of that. So I would just focus on your leading terms, x and x squared. Think about what you would have to multiply x by to turn it into x squared. Well, the answer to that would just be x. If you multiply x times x, you'll get x squared. So we'll multiply this by x. X plus 3 times x is going to be x squared plus 3x. So again, I just multiplied this by x because I really wanted to focus on getting rid of this x squared. Just like before, we have to subtract this. So subtract these away. X squared minus x squared is nothing. 7x minus 3x, well, that would be 4x. And then just for fun, let's drop down this plus 17. Now, the next step is we have to think about how many times x plus 3 is going to go into 4x plus 17. Now, once again, just focus on your first terms. How many times does x go into 4x? Well, that's pretty clear. That's just going to go in 4 times, right? So we'll say plus 4 up here. Multiply 4 by all this. That'll give us 4x plus 4 times 3 is 12. So 4x plus 12. And as usual, subtract. 4x minus 4x is nothing. And then 17 minus 12, well, that's 5. Now, you might be able to guess at this point here, there's nothing that we can do to fit x plus 3 into 5. So that right there, that number, that's going to be our remainder. So this up here, this x plus 4, this is what we would call our quotient. It's our answer when we were dividing. And this one down here, that's our remainder. Now, if we were to show this as a division statement, remember, just going back, we can show this in one of two different ways. We can either show it this way, or we can show it this way. I'm going to be honest, I always just use this one on the left. So what we're going to do is we're going to write the division statement as your original polynomial, x squared plus 7x plus 17, divided by x plus 3, equals your quotient, which is x plus 4. That was our answer there, plus the remainder over whatever you were dividing by. So this will be plus 5 over x plus 3. And that's it. That's our division statement right there. That just shows us that if we were to divide this polynomial by this binomial, we'd get x plus 4 plus this little bit of a difference in here as well. Now you might be wondering, why do we care about this? What is this used for? Well, as we go a little further in this unit, we're going to talk about actually factoring really large polynomials. So if we know how to divide these smaller ones, we're going to be at a much bigger advantage. Anyway, moving on. Next question. Once again, I want us to use long division on this one. P of x equals x squared minus 9, and we want to divide it by x minus 3. Now, I put a hint in here. There's no x term. There's x squared, and then it jumps right to a constant. If you don't have an x term, it's a really good idea to just fill it in anyway, using a 0 in long division. So in other words, call it 0x. Let me show you what I mean. Let's write what we're dividing first. So it's x squared. Let's not forget about our x. So I'll say plus 0x and then minus 9. So this whole thing here is the same thing as what we're dividing, right? Now put this in a box, x minus 3 on the outside, and now we can go to town on this one. Remember, just focus on your leading coefficients. How many times does x go into x squared? Well, the answer to that is just x times. So if we multiply x by this, we'll have x squared minus 3x. And remember, we're subtracting. X squared minus x squared is nothing. This one, you got to be careful. 0x minus negative 3x. 0x minus negative 3x, that's actually positive 3x. It's a double negative there, right? So we're actually adding 3x. Now we'll drop down this next term. So drop down the minus 9. Ask yourself again, how many times does x go into 3x? Well, the answer to that is 3 times, more specifically positive 3 times. So we'll say x plus 3. 3 times all this is 3x. And then 3 times minus 3 is minus 9. And look at that. If we're subtracting this, 3x minus 3x is nothing. Negative 9 minus negative 9 is also nothing. That's amazing. Our quotient is this number up on top. What's so amazing about this, though, is our remainder here. Our remainder is 0. If you have no remainder, that means this fit in there perfectly. So to write this as a division statement, we can say x squared minus 9. I won't worry about the 0. We're all done the division now, right? So x squared minus 9 divided by x minus 3 equals our quotient, which is x plus 3. And then our remainder was 0. So you could say plus 0 over x minus 3, but that would be useless because 0 over x minus 3, that doesn't do anything at all, right? So there's our division statement. If we were to divide x squared minus 9 by x minus 3, you'd get x plus 3. Awesome. Now for the fun part, synthetic division. Now, as scary of a name as synthetic division is, like that sounds terrifying, I can pretty much guarantee, knock on wood, I think I can pretty much guarantee, I should say, that you guys are going to like this a little bit more than long division. Long division is fine. That was just totally okay. But the big downside is if you were dividing by a huge polynomial here, like if this was like an x to the power of 5 or something, you would be at this all day. This would take a long time. It would staircase down your whole page. It'd be a mess. Synthetic division works way better for those bigger order polynomials. Now, it's difficult to break down the process as step-by-step instructions. Instead, let's see an example. I'll show you how this works. So here's a much larger polynomial, 2x cubed plus 3x squared minus 4x plus 15, and we're dividing it once again by a binomial, x plus 3, this time using synthetic division. Here's how this works. Take a look at your big polynomial that you're dividing. First of all, make sure that they're written in proper order of degree of x. So x cubed, x squared, x to the power 1, and then no x at all. That's good. We need it in that order. Also, make sure you're not missing any. Remember on that last one over here, we were missing an x. You have to take that into consideration as well. Make sure you're not missing anything. All of that checks out here. We're not missing any. We're in decreasing order. We're good. Now that we've checked that over, it takes 2 seconds to do that. List out the coefficients in their orders and watch the positives and negatives here because those are important too. So we're going to list them in a horizontal line. Watch this. It'll be 2, give a little bit of space here, 3, -4, 15. Next thing you do, this is going to seem really random. We're going to put this in a box, but it's not the same kind of box as before. It's going to be a box like this. Start with a line over here. Give yourself a good amount of space underneath, and then draw a line straight across over here. Last thing that we got to do here is we have to see what we're dividing by. Well, we're dividing by x plus 3. Just take the 3 over here and plop it right in front. Now it's positive 3 because we said x plus 3. So what you see is what you put. So I'm putting a 3 right there. And then, of course, I just put a minus sign here because we're going to start some subtraction. Here's how this works. This is like a big cross-stitching kind of pattern. It's actually kind of cool. To do synthetic division, you drop down the first number. So this 2 drops down here. And then you do a cross-stitching pattern where you're multiplying this times this and then subtracting it through. Watch what I do. It's going to be 3 times 2. That's going to give me 6. So I multiplied it. Maybe I'll even go times there, right? You don't have to draw this arrow. I'm just showing you. 3 times 2 is 6. 3 minus 6 is -3. 3 times -3 is -9. -4 minus -9, well, that would be +5. 3 times 5 is 15. And what do you know there? 15 minus 15, that is 0. And the reason I say what do you know there, that's actually quite interesting. How we interpret these numbers now is we actually need to read them from right to left. We're going to read them this way. The number furthest to the right represents your remainder. So 0 in this case, that's why I was kind of interested about that. 0 is actually our remainder here. The next number is your constant, so it's just your number. The next number is your x. The next number after that is your x squared. So basically what this means is when we divide this big polynomial by x plus 3, what we get is we get 2x squared minus 3x plus 5. And it's plus 5 because that was a +5 there. And then there is a remainder of 0. Really quite useful, right? So if we were to write this as a division statement, we can say 2x cubed plus 3x squared minus 4x plus 15, all divided by x plus 3, equals our quotient, which is 2x squared minus 3x plus 5, and then plus our remainder over what we were dividing by, but the remainder was 0, so we don't have to worry about that here either. Synthetic division is weird, right? It's a really weird setup. You might be looking at this now and going, hey, you know what? No, long division is easier. But trust me on this one, once you get to really big polynomials, synthetic division saves you a ton of steps and a ton of time and a ton of page room, right? So you don't really want to use long division on really big ones if you don't have to. Synthetic division is certainly worth a little bit of extra effort to learn. So just some things to remember. To do synthetic division, you write down just the coefficients of each term in a horizontal row. If there are missing degrees, you add zeros for those terms. What you see in the binomial, this is really important because people seem to always mix this up. What you see in the binomial is what you write down on the left side. So if it was x minus 7, you'd write -7 on the left-hand side, right? Then you multiply, subtract, and repeat. That's that cross-stitching kind of pattern. And then the numbers you get at the end need to be read from right to left. They represent the remainder, the constant, the x squared, and so on if you had more, right? Let's do another one. You can follow along as we do this one unless you feel really bold and want to give it a try on your own. First of all, step number 1, list your coefficients. Make sure that you're not missing any. Notice in this one, we go from x cubed to x. We totally are missing our x squared here. So really there's a plus 0x squared that's hidden there. So if I'm going to write out my coefficients, the coefficient in front of x cubed is 1. So I'll write 1. And then 0 is in front of x squared, so 0. And then -10. And then +6. Draw yourself the box, leave some room down below it. And then what you put over here on the left-hand side is just whatever you see in your binomial. Well, I see x plus 4, so I'm going to put a +4 here, and we always subtract. Drop down that first term, so the 1's going to drop down here, and then you start that cross-stitching pattern, right? So 4 times 1 is 4. 0 minus, maybe I should draw an arrow there. 0 minus 4 is -4. 4 times -4 is -16. That's how that went there. 4 times -4, right? -10 minus -16, well, that's going to be +6. And then 4 times +6 is 24. 6 minus 24, well, that's -18. So this time around, we weren't so lucky. This time around, we did have a remainder. So this number over here is our remainder. Then we have our constant. Then we have our x. And then we have our x squared. We just build up in terms of degree of x as we go from right to left. And it's important you start on the right because otherwise if you start on your left, how do you know you're starting at x squared there? How do you know you're not starting at x cubed or x4? It's always a good idea to start on the right because the one furthest to the right, always the remainder. We want to write this out properly though. So the actual answer to this is if we were to divide that, it's going to equal x squared minus 4x plus 6 with a remainder of -18. If you wanted to write that as a division statement, be my guest. It doesn't ask for it, so I didn't bother here, but it is up to you. So that right there is the quotient and the remainder. Now, speaking of remainder, there's actually a very useful trick in math for figuring out, the remainder of a certain function. So when a polynomial p of x is divided by a binomial in the form x minus a, very key there, x minus a, then the remainder will just be the value of p of a. Now, what this means, in other words, is if you plug a from x minus a, so if this was x minus 5, and if you plugged in 5 into p of x, the answer you get to that is actually your remainder. There's some really interesting things we're going to do later on with this. There's some complications that show up on a graph related to this. We'll deal with that when we get to it, but this is actually something that's pretty useful. So how could the remainder theorem have told us the remainder in that last example? Well, let's look at what we were dividing by before. In the last example, we were dividing by x plus 4. Well, remember, in this remainder theorem, we need to have it in the form x minus a. So really, it's like we were doing x minus negative 4. So I guess you could say a was negative 4 in that last example, because it was x plus 4, same thing as x minus negative 4. So if a was minus 4 here, we could have just plugged in negative 4 into the polynomial. Well, the polynomial we had before was x cubed minus 10x. Well, what was it? Plus 6. Yep, plus 6. So that was our polynomial before. If we plug in negative 4 into this, let's see if it gives us the same number that we got as a remainder. So we have negative 4 cubed. Important to have that in brackets because it's negative 4 times itself 3 times. Minus 10 times negative 4 plus 6. Let's evaluate this. Well, negative 4 in brackets cubed, I'm pretty sure that's negative 64. And then minus 10 times negative 4 is negative 40, so minus negative 40, and then plus 6. Well, negative 64 minus negative 40 is negative 24, so we have negative 24 plus 6, and negative 24 plus 6, look at this. It actually is negative 18. So in other words, remainder theorem, it worked just fine there, as long as you were only interested in finding that remainder of negative 18 that we had before. All right, so here's a few examples with remainder theorem. It's just a pretty quick thing to get through. A calculator would be handy. What is the remainder when 11x minus 4x squared plus 7 is divided by x minus 3? Well, notice this is in your proper x minus a form, so we can just plug in x equals 3 into our polynomial, and it'll tell us our remainder. Just by the way, the logic by this is you want to see basically where this is going to equal 0. So if you have x minus 3, then you want to plug in x as 3 because it makes that whole thing 0. Anyway, plug 3 into this. So it's going to be 11 times 3 minus 4 times 3 squared plus 7. You know what? I'll just use a calculator here. I don't have it all figured out already. So 11 times 3 minus 4 times 3 squared plus 7. Well, what I got as a remainder is I got 4. So 4 should be the remainder if you divide this by this. And before you ask, you don't need to have your function here in its proper order because we went from x to x squared and then we went back to a constant. That doesn't matter. That only matters if you're doing your division, right? Otherwise, you just plug a number in and you're good, right? Anyway, moving on. Oh, this one's a bit of a challenge. So what is the value of k if the remainder is 3 for this expression right here, this polynomial, and there's k right there, divided by this binomial right here, and the remainder we know is 3. Well, here's something interesting about this. Since we know the remainder is 3, then from the remainder theorem, that tells us if we plug in x is equal to 1, that should be plugging into here, that should be spitting out a remainder of 3. Let's give it a try. So if I plug in x as 1, this is going to give me 1 cubed plus 4 times 1 squared minus 1 plus k, whatever that is, equals the remainder, which we were told is 3. Let's clean this up a little bit. 1 cubed is just 1, plus 4 times 1 squared is 4, minus 1 plus k equals 3. Clean this left-hand side up completely. 1 plus 4 is 5, minus 1 is 4. So we have 4 plus k equals 3. We're almost there. We can solve for k now. Minus 4 on both sides. We have k equals negative 1. So the true value of that polynomial we have up there is x cubed plus 4x squared minus x, and then plus negative 1, or in other words, minus 1. Perfect. Awesome. All right. Almost done. This one's kind of tricky. This one's kind of more of a graphical way of looking at this. So the following graph here, this red graph right here, represents the function f of x equals x squared plus 3x minus 4. Without using remainder theorem directly, determine the remainder of the following division statements. So we're dividing by x minus 2 in the first part and x plus 4 in the second part. Now, if we were to use remainder theorem, I'd be plugging in x equals 2 here, and I'd be plugging in x equals negative 4 here. I'd be plugging it straight into this function and seeing what it gives me. But we have a graph given to us right there. We could actually just do that ourselves. So since what we're really doing is we're plugging in x equals 2, why don't we just look at where the graph is x equals 2? Well, if I plug in x is 2 here, x is 2 is over there, and the graph tells us that's up here at 6. So when I plug in x equals 2 into our function, which is how you would check this with remainder theorem, if I plug in x is 2 into the function, that gives me 6. So 6 would be my remainder if I were to divide that big function right here by x minus 2. So again, that's just the remainder. It's just the remainder theorem, right? What about this one? X plus 4 is the one we're checking. So we got to check x equals -4. Well, if you look on your graph, x is -4. That's right here. The y value on that is 0. So the remainder in this case would be 0. Now the last question there, when we find out, or when we find that the remainder is 0 when dividing polynomials, what is the significance of that point? So in other words, this x plus 4 here, what is the significance of that on our graph? Well, I think it's pretty clear. The remainder was 0. That's technically an x-intercept. So that is an x-intercept. In other words, it's called a 0. And even better yet, it's a factor if you were to get to go that far. But we'll just worry about it being an x-intercept for now. We'll build on that as we go. And look at that. That's one of our quickest lessons we've had so far. That's always good. So page 124, questions 2 to 10 and 14. That's what I need you to focus on. It is very important that we get good practice at this. I would highly suggest you focus on synthetic division rather than polynomial long division. I know how set in our ways we can be, but believe me, synthetic division is going to save you a lot of time in the long run. But again, up to you. Long division is conceptually easier to understand for some people. And if you are someone who just wants to stick through that, by all means, I don't mind. Tomorrow, though, we're going to expand these ideas and gain more practice. If you need any extra help, just let me know.